All right, welcome to carboxylic acids part 5 or chapter 17, esters. So let's look at esters and some of their derivatives, how to make them and what they're useful for. So the first thing we need to do is move on to our first slide. So when we first looked at these reactions, we looked at the nucleophilic acyl substitution reaction. And we know that we can convert from a more reactive acid derivative to a less reactive acid derivative based on which leaving group is better. So if we look at our mechanism again, we have attack by the nucleophile to form our tetrahedral intermediate. In our tetrahedral intermediate, our hydrogen can transfer from our nucleophile to our leaving group to make it a better or worse leaving group. And then once the leaving group leaves, we have that substitution reaction. Again, with aldehydes and ketones, we don't get substitution, we only get addition reactions. Okay, so let's see how that affects our formation of carboxylic acid esters. Okay, so again, the whole series of reactions we looked at is we formed acid chlorides, we formed anhydrides, and then esters and amides. So let's talk first about the Fischer esterification. Okay, in the Fischer esterification, we have treatment of carboxylic acid with an alcohol in the presence of an acid catalyst to form an ester. And so this is an equilibrium reaction that is driven to the ester in this direction or the right by having the water removed or having a lot of the alcohol. If you think about it, this can also act as a nucleophile and drive the reaction back. So by having an excess of the alcohol, you're able to drive the reaction to the right. So in the case of here, we have acetic acid or vinegar plus ethanol, and we're using just a drop of sulfuric acid catalyst to create something like ethyl acetate and water. Okay, in the case, the second case, we have benzoic acid, methanol, to make methyl benzoate. Methyl benzoate is used as a preservative in a lot of things, and again, it forms water as well. So if you can remove the water by having the reaction happen at higher than the boiling point of water, or have an excess of the alcohol, you can drive the reaction forward. So the mechanism is kind of what we'd expect for having an acid catalyzed system. We first form a hydronium ion, which then protonates the carboxylic acid derivative to give us this group here. What this group here gives us is it makes it so that it's much easier to attack our partially positive with our neutral nucleophile. So remember, our alcohol here is a neutral nucleophile, so we kind of need to wait around until it's activated to give us our tetrahedral species here. Okay. Once we form this tetrahedral species here, we have to figure out which is going to be the better leaving group. So in the case of this, if the alcohol is protonated, it's the better leaving group. But if we transfer the proton to one of the hydroxides here, it makes water the better leaving group. And so by a simple proton transfer, we can have water leave to give us back our trigonal planar derivative, and then our proton can be transferred back to any base in the system, yielding our neutral compound. Once we form this neutral compound, we could protonate it and have it go backwards again. But again, if it's attacked by the methanol, it's going to give us this product back. If it's not attacked by methanol, it's going to give us our starting materials. That's why every single step in here is reversible. You can go back and forth through all these steps. And so the thing that's driving this thing forward is having an excess amount of the alcohol available to us. Okay, so now that we can make the esters, and it's most commonly done in that way, we can actually go the opposite direction on purpose. We can take an ester we have, and by adding excess water and either an acid catalyst or a base catalyst, we will create, if in the case of the acid catalyst, we will create the carboxylic acid. And in the case of a base catalyst, we're going to end up with the carboxylate ion and the alcohol that's generated from that. Okay. In addition, we can also convert an ester to an amide. Remember, we can go from more reactive to less reactive, but we can't go the other way around. Well, esters are just above amides on our list here. So we can take any nitrogen that is nucleophilic, we can then displace the R group here to give us an alcohol in the end here. So if you have an ammonia, you can get to a primary amine, amide. If you have a primary amine, you can get to a secondary amide. And if you have a secondary amine, you can get a tertiary amide. If you have a tertiary amine, you will only make a salt. You will not actually do the displacement because there's no proton to transfer to the leaving group. Okay, so there's another reaction we can do. If we can convert the carboxylic acid to the ester, and we can convert the ester to an amide, we can also convert one ester to another ester. And the key to doing this is if we have a high boiling ester and a high boiling alcohol, and we add an acid catalyst right here, we can actually drive the reaction in this direction by having the lower boiling alcohol boil out of solution. So for example, if we have this compound here, which is the methyl acrylate, so this right here is the acrylic acid, and we have the methyl group here is our alcohol, and we take butanol here. Methanol boils at 54 degrees. Right here, butanol boils at well over 100 degrees. And so what we can do is just by having a drop of acid catalyst right here and refluxing it at above 54 degrees, because that's where the methanol is going to start to boil out of the reaction, we can drive it to completion right here. So what's helping us here is just like in the presence of where we were trying to form an ester in the presence of water, if we drove the water off, that would drive the reaction, or if we had a high concentration alcohol. In this case, because we're driving the lower boiling alcohol off, we can drive the reaction to the right. Okay, so how does that work? In an acid catalyzed system, the first thing, of course, we're going to do is we're going to protonate our compound. So we protonate our carbonyl here such that we can have attack by our water or our alcohol. And once we form that, now we can have a proton transfer from our protonated alcohol species to any base in the system, yielding this compound here, our tetrahedral system. And now, depending on which is the better leaving group, we can have this hydroxide or that hydroxide leave. Or in this case here, if we protonate the alcohol, we can actually regenerate our carboxylic acid. So let's protonate our alcohol in these species here, right here, making it now the best leaving group of the set because it'll leave as a neutral species. We have loss of alcohol as the neutral species, and then we regain our acid catalyst to give us our carboxylic acid plus our acid catalyst plus our original starting alcohol. Now, this is again driven by the fact that we have to protonate our species to create our tetrahedral center, and then by transferring the proton to one of these species, it'll drive the reaction forward. If you end up protonating the hydroxides here, it's just going to go back to the original material. If you protonate the alcohol or the ether right here, it'll drive it to completion. So it's all about trying to force the reaction to go in the direction you want. Okay, so if we're looking at basic hydrolysis, it's actually slightly different. We're actually using hydroxide as a nucleophile. And so when we form our intermediate species here, we have a comparison between having hydroxide leave or having the alkoxide leave. And typically, the alkoxide is a weaker base, and therefore what we can have happen is that the alkoxide will leave and it'll create our salt of our carboxylate and our ester, and then when we protonate our system, we end up with our carboxylic acid center. Again, this is hydroxide promoted, not catalyzed, because we have to add a single hydroxide for every single molecule we need to have happen. So it is it's an actual reaction. It is basic hydrolysis, not catalysis. So you need at least one equivalent, sometimes two equivalents to get these reactions to go to completion. And that is it for esters. Our next chapter is 17.6 amides.